Hello, everyone. Welcome to the July talk in our seminar series, which aims to provide accessible introductions to some of the most significant mathematical theorems of the 21st century. Today's talk will last about 45-50 minutes, followed by time for questions and discussions. Please feel free to type your questions or comments at any time in the meeting chat. It is my great pleasure to introduce our today's speaker. Professor Oleg Pikhurko is a leading mathematician whose work has made major contributions to external combinatorics, graph theory, random structures, and related areas of mathematics. In this talk, he will discuss the famous problem of squaring the circle. The problem asks whether a disk can be cut into finitely many pieces, and then the pieces are rearranged to form a square of the same area. This looks a bit paradoxical. The talk will outline the history of this classical problem from its geometric origins to recent breakthroughs. I am now happy to hand over to our speaker.
Yeah, thank you, Bogdan, for the introduction and for the invitation. It's a very nice series, and it's a great honor to talk here. Yes, so I'll be talking about squaring circle, but not in the way that ancient Greeks tried to do it with compass and ruler, but as Bogdan mentioned, by equidecompositions. Okay, now I'll try to get, maybe hopefully it will work. Yeah, and so let me start with definition. So I have some two sets, A and B, in some Euclidean space, k-dimensional R2k, and I call them equidecomposable and write A sigma B. If I can find partition of A and B into n parts, and for every index I, there exists some isometry of R2k, which maps AI to BI. So in other words, I want to split A into parts, rearrange them using isometries, and get exactly a copy of B. So that's the key definition. Unfortunately, it's not easy to come up with non-trivial examples. So here is an almost example when I try to convert a triangle into rectangle. So given a triangle, you draw like horizontal line at the middle, and then you have two more little triangles, and you just try to flip them to the sides, and then you get a rectangle about half of the height. It's not quite exactly the definition above, because if you look, for example, at these 2 points, then they'll be mapped into the same one. But it's close enough, and this is kind of notion which used in geometry in ancient times. Like this could be a way how to prove formula for area of a triangle. And like famous theorem about 2 centuries ago from 19th century is that if in the plane you have like polygons of the same area, then they're equivalent under this kind of equidecomposition where you have like straight line cuts and you don't care about the boundaries. And then later it was observed by Tarski that in fact you can kind of, if you're happy to add extra parts, then you can absorb or create boundary very easily for polygonal pieces. So in fact, yeah, this example can be converted into being equidecomposable. Maybe you won't have 3 parts, you have probably a few more. Yeah, and like probably the most famous theorem in this area is by Banach-Tarski. It's 20th century. So if you take R to the k, when k is at least 3, and take any 2 sets which are bounded and each has an empty interior, then they are equidecomposable. And in particular case, if you take unit ball in R23, then it can be doubled. It's equidecomposable to 2 copies of unit ball. Sometimes it's formulated that a P is equidecomposable to a sun. It's one of the consequences of the theorem. And actually, it was not just a curiosity. The motivation was to understand the theory of the back measure. So as far as I understand at that time, like it was the back measure already was many convergence theorems were proved, and people realized that it's like a big important concept. And many questions at that time were open about like when we take definition of say Lebesgue measurable sets, you cannot define it for every set. Like Vitali set, it shows it's impossible. But then you can ask, okay, if I maybe weaken my axioms that a measure has to satisfy, so the back measure is countably additive. If you have countably many sets which are disjoint, then measure of the union should be sum. And then question was like, what happens if you only insist on finitely additivity? Which means if you take any finite number of sets which are disjoint and take like mean, or let's call it mean, to distinguish from measure, and take kind of values of each and add it up, then it should be the value of the union. And then the question was, okay, now we have like a weakened option that we require of our measure. Can it be defined for all sets? Yeah, and Banach-Tarski paradox shows it's impossible, because if one exists, it assigns some positive measure to a ball, but then like if it's isometry invariant, then it has to assign the same measure to two copies of the ball, which contradicts finite additivity. And also earlier Hausdorff observed that on the surface of the sphere in dimension 3 or higher, so two-dimensional sphere is already okay, you can prove similar paradoxes, but his paradoxes were stated a bit different. Roughly, he proved that 1/2 of the sphere is equal to 1/3 of the sphere, which is also enough to rule out means on the surface of the sphere, defined on all sets. And of course, it sounds paradoxical, and the reason is because both proofs use kind of crucially rely on the axiom of choice. So this is some small recap. But as I mentioned, this applies only in dimension 3 or higher. So you can ask what happens in dimensions 2 or even 1. And Banach proved that in smaller dimensional case, like plane on the line, if you have two sets and each of them is Lebesgue measurable, and you can equidecompose A to B, even if you use axiom of choice, so intermediate pieces need not be measurable. At the end, conclusion would be it's only possible if a measure of A is the same as measure of B. So in some sense, you cannot increase or change measure of sets under equidecompositions, even if your intermediate pieces are arbitrary. In particular, you cannot double a disk. Yeah, and this result prompted the famous Tarski circle squaring problem. He said, okay, in the plane, we know we cannot change area or measure. So if you take two simple figures like a disk and square of the same area, are they equidecomposable? And this problem turned out to be quite difficult. So there was some partial progress. So von Neumann showed, okay, if you allow modern isometries, if you allow affine transformation, then the answer is yes. And this was very influential paper where he also introduced notion of amenable group, which is very important in modern mathematics. And then there are a couple of other results, negative, if you put some extra constraint. Like, for example, Siso congruence basically says that each piece is topologically homomorphic to a disk. And some negative result by Gardner. Until like 65 years later, it was proved by Latzkovich that the answer is yes. And even like quite remarkably, his result says you can equidecompose a disk into a square, and you don't need to use rotations. So every piece you can just translate without rotating. So that's this result by Laskovich. And in fact, then he wrote a series of 3 papers, and in 2 later papers he proved a more general result. So in order to state it, I have to give some definitions, and actually this definition will be used later. So I'd like to define or recall definition of the upper Minkowski dimension. Also in some sources it's called the box dimension. So you have some set X in R to the K, and for every real epsilon, you partition into a grid of length side epsilon. So here's the first picture. So my X is the cycle boundary of a disk, and then epsilon is side length of every little square, and then n epsilon of X counts how many pieces intersect X. So in this case, n epsilon of X counts number of little squares. And then to define dimension of X, dim box of X, you let epsilon tend to 0, and then you divide log of n epsilon of X by log 1 over epsilon. And maybe a bit better way kind of to think about this way. So you look at infimum of D, such that if you take this function n of epsilon of X, it grows as 1 over epsilon to power D, roughly up to some small error term. Yeah, and it's a priori, it's not clear that limit exists, so we have to take lim sup or lim inf. So in this definition, we take lim sup, and that's why it's called upper Minkowski dimension. Because on different scale, your set could be fractal of different dimension. And for example, if you look at the boundary of the disk, so delta means topological boundary, then basically dimension is 1, because if you go along, then for every unit length, you probably stay in the stripe of width to epsilon. So in total, you would probably cut it most constant as epsilon different squares. So dimension of upper Minkowski dimension of a cycle, say, is 1, which coincides with our intuition. And then why is it good if boundary of a set has small upper Minkowski dimension? The reason is because then we can approximate it really well by boxes. So by box, I would mean just product of intervals. So I'm in Rk, I take any k intervals of different lengths possibly, and just convenient to make them half open. Doesn't matter really. And then nice result says if your box dimension of boundary of X is strictly less than k, so k is always an upper bound. Because if we talk about bounded sets X, so it intersects at most some epsilon to k times constant different number of boxes. But if it happens to be strictly less, then you can approximate very well by boxes. And this picture on the left, on the top left, actually shows how you do it. So here's the formal statement. So you can sandwich X between two sets, K and U, such that difference what's in U but not in K has small measure, so or area at most delta. And the total number of boxes is also quite small. And so in this picture, your set U will be just, you take maximal vertical rectangles. So this would be your set U. And then your set K would be U union with these squares. So this is K minus U. It will be union of these squares. And if you do some calculations and you like target arrow as like delta, then you can check, you would get like delta to C minus K boxes. So it's very similar to regularity of the measure, except somehow sets, lower set and upper set, they have very simple structure. And this was crucial in proof by Laskovich. So now I can state his general result, which applies in every RK. K could be even 1, and it's already interesting. So if you take any two bounded sets in R to the K, and each has a box dimension at most less than K, strictly less, and they happen to have the same measure and positive Lebesgue measure, then they are equidecomposable, and in fact, you can use translations only. So that's his more general result, and it applies in particular to cycle squaring, because for square or disk, the boundaries have dimension 1 in R2, which is less than 2. So before I'll talk about more constructive results, let me just give sketch idea how his proof proceeds. And actually that's how I came into this area. In a way, kind of equidecomposition, once you fix which isometries you use, you can restate it as a graph matching problem. When you have a bipartite graph and you want to find perfect matching, so specifically, suppose you fix some isometries, gamma 1, gamma n, then you can and you have two parts A and B, which you want to ask if they're equidecomposable or not. Then you can define a bipartite graph, which we'll call Kelly H. So its parts are A and B, and edges you take pairs X from A, Y from B, such that X is mapped to Y by some of your chosen isometries. So maybe here's illustration. So perhaps this is A, square is B, and maybe your gamma 1 is translation by this vector. Then your H set, you put every X and every Y, such that Y is translation of X by gamma 1. And you do it for every gamma I. So in total, you would have infinite graph, A, B are infinite in general, but every degree will be finite. At most, this number capital N. And now, what is a matching in this graph? So you want to find a collection of edges, now to share a vertex. So to specify a matching, you have to tell me just which vertices in the, say, in left, in A, use gamma 1, then which vertices use gamma 2, and so on. So you can encode them by subsets A1, AN, which are disjoint, because it's a matching, so every vertex uses at most one edge. But then property is if you also on the other side, you cannot have vertex of degree 2. So their images have to be disjoint, and vice versa. If you have such sets, and then you take corresponding edges, then you have a matching. And in particular, if you can find a perfect matching in this graph, which means every vertex in the left is matched to every vertex to the right and vice versa, then in fact AB are equidecomposable. And these sets, A1, AN, give you the pieces which you can use. So takeaway message here is if you know which rotations you're going to use, then equidecomposition reduces to finding a perfect matching in some graph. So next slide will be quite heavy in definitions, but I'll try to walk you through it. And so, because first question which Laskovich faced was how do we choose these isometries? Yeah, and but before we do this, one useful reduction, which it's much more convenient when you kind of work in compact space, which is symmetric. So instead of working into R to the D, we worked modulo 1. So you can always scale your two sets, so they fit inside unit cube. You can even assume they are disjoint. And then you work modulo 1, so like your underlying space is symmetric. And then what Lashkovich does, given two sets A and B, he fixes some integer, which should be somewhat large. And then he picks random vectors x1, xd in the torus, which means random vectors in the unit cube, except when we add them, we take addition modulo 1. And then actually he proves that if x1, xd are uniformly at random from elements of t to the k independent, then actually typical outcome or probability 1 will have properties which we'll need. So which I'll state in the next slide, but suppose we already fixed some typical outcome, x1, xd, and then having these d vectors, you pick large M, and so far in all these proofs, this M is quite large. And then somehow it's tempting just to take x1, xd for your translations, because we know randomness works very well for many problems. So here it's tempting just to take d random vectors and say these are kind of translations I'm going to use. But in fact, at least we don't know how to prove it with unit random vectors. But what works is once you fix x1, xd, the set of translations which you allow, it is consist of integer combinations of xi's, where each coefficient is at most m in absolute value. So in front of each vector xi, you can put any integer between minus m and m, and you take all these as your translations. So if you look at the number of parts, this would be like to m plus 1 to d. So this grows very fast. Yeah, I'll talk at the end, like what we know about number of parts from these proofs. And then what is your graph? So it's the same graph as on the previous slide. So it's a bipartite graph, still denoted by H, where its parts are A and B. And edges, so here our isometries are translations by some vector. So for every vector from the set Kelly V, I put an edge between A and A plus V, as long as like it joins A to B. And to find equidecomposition, we have to find perfect matching in this graph. But somehow it really helps if you have symmetries, because if you restrict to A to B, you lose all the nice properties. So in this particular case, it's a bit more convenient or much more convenient to work in a different graph. So I'll call it Kelly G. So its vertex set is called torus, which is just cube mod 1. And then what are its edges? You can take any U, and you are allowed to connect by adding linear combination of xi with integer coefficients, but where every coefficient is at most 1. So you can connect U to U plus x1, or to U plus x1 minus x2, and so on. So like if you look at this in ice, you allow L infinity jump of length 1. And somehow, yeah, what is nice that if you, since x1, xd are random, then among these integer combinations, there is no collisions. So in fact, all these vectors for integers and I are different. So you get action of group Z to D on the torus. So what is the action? If you take any element EI, standard vector, then its action is just translated by xi. And in this action, this object is known as the Schreier graph. It's somewhat similar to Cayley graph, except its vertex set is not the group itself, but the space where it acts. And as I said, there are no non-trivial relations between xi's for typical choice of x1, xd. So if you take any connectivity component of a graph G, where every two vertices are connected by a path, then each connectivity component is a copy of Z to D. And what do we want in this graph? We want to equidecompose A to B. So we want to use integer combinations where each coefficient is at most m. So equivalently, if we want to rephrase it in terms of this graph Cayley G, what we look after is a bijection from A to B, such that whatever U I take, it's E inside A. Its image is in the same component, and moreover, inside this graph G, I can go from U to phi of U in at most m steps. Maybe let me pause for a second. Yeah, there are lots of stuff here. So basically, again, we're trying to solve a matching problem, but it happens to be more convenient to work in a bit different graph, where we look at a matching between two specific sets, A and B. And constraint is that if I match somebody from A, its match should be at most distance m. And here is a picture. So maybe suppose we take D equal to, so if you remember, D is number of choices xi. So in this we have x1 and then x2. So somehow that's how we look at connectivity component. And edges are jumps at L infinity distance at most 1. You can take standard one, but it's more convenient to allow diagonals as well. And then in this graph Cayley G, you have some set, maybe call it A, say your disk, blue points, and then you have some other points red, which come from B. And what you want to do, you want to find bijection. And here m is equal to, so our bijection shouldn't move every point more than by 2 in L infinity distance. And in this small picture, here's a possible solution, how you can match A to B. And so now, after this reduction, which is fairly easy, now comes the main work, is to argue that such a bijection exists. And that's a lot of work. And the way Laskovich does it, he proves discrepancy bounds. So what he proves that if you take any big square in this discrete picture, so maybe I'll take this one, 4 by 4 square, then what he proves that number of, in every square on every size, number of blue and number of red points are about the same. And more specifically, he does the following. So first, let me define a discrete L cube, which means I can start at any point U, and then I can move in each xi by any one of L choices, say by integer between 1 and L. So like in the previous picture, it was a square. So 2 cube is any square. So here's another example of 2 cube. Even a degenerate one is an example of a cube. And kind of what he proves that if, say, you set A has a box dimension strictly less than K, then Okay, let's ignore this almost every x at the moment. Then for typical x, the following very strong property holds that whatever L cube you take inside this discrete picture, so let's see how many points from A we expect to see. So cube Q has L to the D points, because it's the dimensional and you have an L points on each side. Now, if total measure of the torus is 1, so for example, if measure of A is like 1 over 10, you would expect to see hit A 1 over 10 times. That's how often you hit Q. And his discrepancy estimate says whatever Q you take, it's always much less than boundary of this cube. So you have this discrete cube. And then if you look at its boundary, then it has like L to D minus 1. And he proved that remarkably, somehow, if A has small box dimension, which means I can sandwich it between two very simple sets, if you remember a slide long time ago. And then in fact, his result says inside each such local picture, each color red as well blue is very uniformly distributed. So ergodic theory would tell you that this typically goes to 0 if you scale it, and here like he gives very strong control over what is the error term. And then there's another quite difficult argument where he argues that once you have this discrepancy property, then in fact this graph H, where we have only parts A and B, satisfies the usual hole condition, which means if inside part you take any finite set X, then a number of neighbors of X in the other part is at least size of X. And so for finite graphs, it's enough to have perfect matching. If your graph is infinite, but every vertex has finite degree, then Rado theorem is enough. It also gives you perfect matching, but as such, it uses axiom of choice or compactness, so it's very non-constructive. And so Laskovich proof very heavily relies on axiom of choice, crucially. And the question kind of which can be asked is, can we square cycle in a constructive way? Okay, so somehow we want to define some notion of regularity or some family of sets where our pieces should belong to. And in descriptive theory, I'll just talk about two classes of sets which appear quite often. So one class of sets which you can consider as constructive are Borel sets. So formal definition is, what is a Borel set? We call it Kelly B. By definition, every open set is a Borel set. And then it should be like smallest collection, which is sigma algebra, which means closed under countable unions and Boolean operations and negation. And there is another like way how to characterize Borel sets, say in unit interval 0, 1, which says that a set is Borel if it can be computed by a countable Boolean seconds of its binary digits. So maybe here's the picture. Suppose I look at the set of reals, and by definition, I take only those x such that in binary I see two consecutive digits 1. And this set is Borel, because if I write sequence of its digits, then I can write this Boolean second at the bottom. It has AND gates and OR, so it's a very simple second. And well, so here I'm allowed infinitely, like this one has infinitely many gates with infinitely many inputs. So it could be infinite second, and well-founded means that if you try to compute final outcome, you don't see infinite chain going down. So kind of the result is always determined. So this kind of nice description of Borel sets. And these sets are regarded by descriptive set theory as nice, definitely. And slightly larger collection is Lebesgue measurable sets, where basically one of the equivalent definitions would be Borel, except on the set of measure 0, you don't care. You can do whatever you want. So how do we define a null set? Well, any set, if you give me any epsilon, I can find it by countably many boxes whose total volume is at most epsilon. And for example, every countable set is null set, because I can take boxes whose volume decreases geometrically. And then Lebesgue measurable set, by definition, it's the smallest sigma algebra, which contains all Borel sets, and also every null set is included. And then it requires a bit of proof. In fact, you can prove that equivalently, a set is Lebesgue measurable if and only if you can find some Borel set B such that the symmetric difference is null. So in some sense, if you find equidecomposition with Lebesgue measurable sets, it means it's constructive, except on some set of measure 0, on a null set, you probably applied axiom of choice, but we don't care. So these are like two nice families of sets, which are very natural. And so the question would be, can we guarantee pieces in cycle squaring which are from one of these two families? And so here again, a long slide with summary of results. So assumptions are the same as in theorem of Lackovich. We have two bounded sets. The topological boundaries have small box dimension. They have the same positive measure. And conclusion which we'd like to have that we can equidecompose A with B, such that we have some finitely many pieces, A1 up to A capital N, and we use translations. So Lackovich proved it's possible. And now question is, can we find more regular sets? And so first result was with Lukasz Grabowski and Andrzej Mate. We proved that you can do Lebesgue measurable sets, which, as I said, means you're allowed to apply axiom of choice, but it's restricted to a null set. And then Marx and Uringer strengthened this, and they proved that, in fact, you can make each set to be Borel by introducing many beautiful new ideas. And then more recently, we proved that, in particular, cycle squaring, you can guarantee that each piece is nice in the sense it has a boundary of small dimension, which means you can approximate it very well by boxes. And also, okay, it's a Borel. If A and B are Borel, then each piece will be Borel. So it implies this result of Marx-Unger. But it also says that somehow you can measure how complicated Borel set is, how many times you have to apply countable unions operation. So here, like this result says roughly, we only go one level up in this hierarchy. So you start with your sets A and B, and you start with nice sets as open sets. You're allowed to take the Boolean operations and translate. You have to pass to countable union, you can think as a limit only once, and then you apply Boolean operation, and that's a family of sets which contains every piece. And in particular, if you apply this theorem to cycle squaring, then you know it's at more less than 2, but we computed explicit bound. So it's still below 2, but it's not very impressive number. It's only slightly below 2. And then if you look at this formula and say cycle and square are closed sets, then you can in fact show that each AI is a Boolean combination of so-called F-sigma sets. So they're quite nice. They're just countable unions of closed sets. So in some sense, in this Borel hierarchy, parts are have quite simple structure. And more recently, Unger, Varadarajan, and Weilacher, they proved that in fact, in our result, you can remove this 1b. So they kind of a bit lower complexity. They couldn't get also this property of having small boundary. And in particular, like if you apply it to second squaring, they can guarantee that each piece is already an F-sigma, countable union of closed sets, and its complement is also in F-sigma. Or in other words, each piece is both F-sigma and G-delta set, the complementary family. Yes, so these are like results up to date. And the way these results are proved is via using methods and tools from descriptive combinatorics. Which is a relatively recent area, but it's quite active. So what is the typical problem of descriptive combinatorics? In a typical instance, you we operate with graphs on topological spaces, typically infinite. So vertex set could be interval or some version of contour set. And let's assume that all degrees are finite, like in the previous case. You have finitely many isometries, so each degree is finite. And then what we would like to, what kind of problems we solve, the ones where kind of validity could be checked locally, so-called locally checkable problems. For example, perfect matching is an example. Because how can I check if matching is perfect? Well, every vertex has to be happy. And for vertex to be happy, it's matched by exactly one other vertex. Or for example, if I ask about maximal independent set, again, it's property which you can check locally. If I tell you the set, then every vertex has checked two properties. Like if I'm in the set, none of my neighbors is. So set is independent. And on the other hand, if I'm not in the set, then at least one of my neighbors should be in the set. So this you can kind of look at your radius one neighborhood and then decide if these two properties hold. Yeah, and many other properties can be recast as locally checkable problems. And somehow typical question, again, can you find a constructive solution? Where, for example, each color class is a Borel or Lebesgue measurable set. Yeah, and this area has many applications. So where you see such object directly are like Borel actions of groups. On a probability theory, you have a factor of ID problem. Where, for example, you take infinite graph Z2, and on each vertex you have independent random seed, real variable xi. And now you can want to construct some function like independent set based on these labels. And also, like another surprising and very recent connection is this kind of very abstract infinite object. Actually, the methods that people developed are useful in theoretical computer science for distributed algorithms. And in fact, there are not only methods, but there are some direct transfer results. But if some class of problems has nice solution, then finite problems in computer science, they have like fast local algorithm. So that's kind of slide for advertisement. Now, if you got lost, so now it's a good time to wake up. So I'll try to, again, briefly recall what we're trying to prove. So we work inside torus, which means reals modulo 1, k-dimensional. We have some d vectors, x1, xd. Now we allow to use translations which are integer combinations of xi, where each coefficient is between minus m and m. So let's maybe order all these vectors v1, vn, just number them in some way. And then we have this graph KLG. So now I'll switch to this graph KLG, where a vertex set is the torus itself, and edges inside this vectors xi, I can jump at most distance 1 in each coordinate. So I can add any integer combination where each coefficient is at most 1, minus 1, 0, or plus 1. Then I have two sets A and B, and I want to find a bijection between A and B. So here again, this picture we saw before. So here D is equal to, and you have red and blue points. Here again, M is equal to, you can go distance 2 in your bijection. And like here, like small piece of solution, like in this particular case. And somehow we want to find this bijection constructively. So one way, of course, your sets A and B, say circle and square, are nice. Also, if you translate them, it's again very regular sets. So, for example, of course, if you take sets like, say, for example, A minus x1, and you intersect with B, how can you check if some point U is inside the set? Let's call it U. Well, it happens if picture at U is like this. So here is U. You are already in A. So maybe let's, okay, A is circle. Then if you, in B, B is a circle. And then if you move U by x1, you should hit A. So to check this property, you have just to check two conditions. You are in B, and if you move in this graph along a fast line, you end in A. So somehow you look at kind of a local function. Or for example, if you have extra set, maybe say B plus 2x, say, okay, again, x1, then you have to check if this belongs to B. So this time you have to look at distance 2. And so you say it's a local function. If to determine value, just look at finite interval. And here maybe some pictures, nice pictures drawn by Andras Mate. So what is like local function at distance 1? It means you look at 9 different points around you. So you take 9 translates of disk and square. So there are 9 disks and 9 squares. And this is Venn diagram. And if you increase R by 2, you basically already see almost like white noise. So as you increase radius R, complexity of sets you get would be very large. So maybe let me just finish this slide and then I'll jump to open questions. So how can you construct bijection? And one way is that greedy algorithm, you can move to this infinite setting quite easily. So suppose you have translations and you want to construct bijection greedily. So for example, first we look at V1 and we say, let's try to take as large as possible set inside A, which could be sent to B using V1. And of course, formula would be just intersection A, B minus V1. So we use this. And then their neighbors are B1. You just take A1 plus V1. Now we move to V2. So again, we want to take as large as possible part of A, which we can still use. We cannot use A1. so we have to subtract it. We cannot hit B1 in B, but otherwise we take as large as possible sets. So that's A2. So basically, if you pick greedily as many as possible points that you can use VI, then you can write simple Boolean formulas. And if you do it for every n, then at the end you would get parts, pieces, which are very nice function of A and B, in fact, local function, according to previous definition. So I suspect I'm running a bit out of time. So maybe I'll give, let's see if I can jump, no, to where's the pages. Okay. Yep.
There was a question, how do you choose n?
So you choose a D large, and then you choose x1, xd. And then you take integer combinations where each coefficient is at most m. So in this picture, n would be to m plus 1 choose d. So usually d is somewhat large, and then m is very large. Let me try to figure out where I can see pages. Okay, I can maybe jump then different viewer. Well, Oh, so here are open questions. So, so maybe it'd be nice to finish with some open questions. As I mentioned in our results, what we get upper bound on dimension like 1.98 something. So can you make it close to 1 or even exactly 1? Then another interesting open question is second squaring possible where each part is just a Boolean combination of open sets? So you can start with any open sets. You can take the finite Boolean combination. Is this enough to square the circle? Another interesting question, which is open, suppose instead of, say, R2, you work on the surface of the sphere. So this is S2, for example. You have nice group of rotations. And again, question would be, if I take two sets which are nice, say maybe spherical cup, one set, and the other set of the same area, some stripe, are they equidecomposable or not? So with Lukasz Grabowski and Andrzej Szmaty, if we are happy to tolerate a null set of errors, then kind of we know the answer is yes, modulo some obvious necessary conditions. But to prove Borel result seems to be very difficult. And then another question, which now doesn't have to do anything with regularity of pieces, is like, what is the smallest number of pieces we can have? So Lackovich in his paper, he wrote that he estimates like 10 to the 40 pieces are enough. More recently, Marx Unger, they wrote self-contained proof of Lackovich with many new nice ideas, and they estimate this to be at most 10 to 5. So 26 is not a lower bound on number of pieces, it's a lower bound on publication year. And best known lower bounds are very bad, so like for example, if you allow rotations, then we know at least 3 pieces are needed. And if you use translations, only at least 4 pieces are needed. And then there is nice, Andras wrote nice computer code where he tried to solve a discrete version. So as a square, he took like pixel picture when you have so many pixels. And then he wrote a disk made of the same number of pixels. And then he experimented, and in fact, if you work modulo 1, then at least in this discretized version, it seems like 5 pieces are enough. So, so for example, here's your big square, and when you move it modulo 1, one piece would be take like this one. Yes, so quite possibly, yeah, you need like a very small number of pieces, but it's just methods are not strong enough, even if you don't care about sets being regular. Yeah, since I'm out of time, I'll probably stop here. Oh, okay. Maybe I'll just put some literature for. Yeah, thank you.
Okay, yeah, thank you for the talk. I now unmute everyone, so you can ask a question by unmuting yourself and then just talk. Or alternatively, if you don't want to talk, you still can type your questions in chat. I will start with my simple question. So what is the number of pieces in your papers?
So in my paper, we didn't estimate it as too much. I saw a talk by Andrew Marks. They had this fast Borel version. They had estimate 10 to 200. But now, okay, maybe I'll just go quickly over this. So like what I would recommend people, if you're interested what to read. So about cycle squaring, like these two are good papers. So this is nice book by Tomkovich-Wagon, which has section on cycle squaring. And then Marx and Unger, they wrote a new proof of Lackovich problem, where they used modern methods, and in particular, in this paper, they have like less than 10 to the 5 pieces, and it's elementary and self-contained. So if you want to read all the details and understand Lackovich proof, yeah, I would highly recommend this. Yeah, and then this are like general kind of service about connection between this descriptive combinatorics and algorithm. And this is a kind of collection of open problems. It's a bit out of dated, but it's still a very good read. Yeah, and there's some kind of summary like methods which I wish I had like when I was studying this area, were just a summary of some basic results if you work about Borel version. So if you kind of decide to work, yeah, that's maybe good point to learn methods.
Okay, thank you. I see Siddharth had a raised hand, yeah? So can you ask your question?
You mentioned towards the beginning of the talk, well, you introduced the notion of upper Minkowski dimension. As I'm sure you're aware, it has some limitations, particularly the fact that it overestimates dimension, especially for sets that have varying local densities. So do the theorems that you mentioned still hold if we use an alternative dimension system like perhaps a Stewart dimension or packing dimension, which handle local density fluctuation much more reliably than Minkowski dimension?
Yeah, this is a very good question. So let me find this result by Lackovich. Just a moment. So this is still his proof. Just a moment. Here's his result, which I mentioned. Yes, so actually, around the time he has paper with some negative examples, and one was the following: suppose you want to replace this condition by something else, and can you? And he has example. If you look at Hausdorff dimension, and you insist that it's smallest possible. It's only k minus 1, then it's not enough. So his example that if you try to replace, say, put Hausdorff dimension, and even if you put a very strong bound, that boundaries have dimension only k minus 1, which is least possible for sets of positive measure, then this result holds. And he has many other examples of negative kind. So somehow this theorem seems to be hard to improve. Yeah. So.
Okay. Can you see chat now? During the talk you could not, but now maybe you can see chat. Because there is a question in the chat.
So this, if I understand correctly, the question is like about why is there a difference between k equal 2 and k equals 3 in dimensions? So kind of short answer is if you look at a group of isometries of R2, then as the group it's amenable. So in the way how Banach proves this result, he shows that exactly opposite of what happens here to prove his impossibility result. So he used Hahn-Banach theorem to argue that in dimensions 2, you can define for every set, every bounded set, you can correspond some number such that this function it's finitely additive. So if you take union of two sets on disjoint, then on disjoint union, it's the sum of the values, and it's invariant under isometries, and it can be defined for every set. So finitely additive means exist in R2, and then since this mean exists, it means if you have two sets which are equidecomposable, then however ugly the pieces are, mean is defined for every piece. And then if you compute value on M and the value of B, by finite additivity is just sum of the pieces. By isometry invariance, it's again sum of the values of the new pieces. So it cannot change, and this mean coincides with the back measure on nice sets. So that's how Banach proved that it's impossible to change measure. So, and now maybe modern proof would use ultrafilters, for example. So you can find almost invariant sets, some sequence which cover whole space. And then for each set, you define mean. Of course, it won't be isometry invariant. But then if you pass to a limit, since these are Follner sets, they have a very small boundary. So you can argue that you would have isometry invariant mean at the end. So the difference is exactly that isometry invariant finitely additive means exist in R2, but not in R3. But also his theorem applies in higher dimension if you use translations only in RK, where K is the 3, but you take translations only, then as the group it's amenable, it's abelian group. So again, this result holds. So basically, short answer is it's group theoretic properties of isometries, whether it's abelian or not, which matters in these cases.
Okay, yeah, thank you. So it seems you answered all the questions. Yeah, it was clarification and the intuitions for the infinite additivity failing in 3D.
Okay, so because if you look at so somehow you can try to do like this ultrafilter approach in R3, for example. Again, you exhaust R3 by larger and larger walls, and you take some ultralimit with respect to ultrafilter, then which property would fail? It will be the translation invariant. Because if you have some shift by gamma, let me just move next page. Yeah, if you have some fixed shift by gamma, and you take a large ball and you translate it, then essentially measure doesn't change, but it won't be a rotation invariant, because on the surface of the sphere, if you look at a group of rotations, it contains F2. And so on the surface of the sphere, you can easily find sets, say half of measure or quarter of measure, such that if you rotate, they move by to disjoint set, for example. So somehow, if you try this ultrafilter approach, it will fail because obtained mean won't be rotation invariant, because group of rotations is so rich, it already contains F2, and F2 is non-amenable paradoxical group.
Okay, thank you. I think the time is already time to finish this. So thank you very much for the interesting talk and for answering the questions. And thank you everybody for coming. Yes, we have seminars once a month. So the next seminar will be in August, in 19th of August. Hope to see you all there. Yeah.
Oh, thank you for coming.